Go.
Okay, so let's now all sum up the relationship between the outer ear, the middle ear, and the inner ear. Okay, so the outer ear extends from the auricle or the pinna up to the eardrum or the tympanic membrane. The middle ear is the tympanic cavity, the air-filled tympanic cavity which connects the ossicles, and it's in relation with the inner ear. Or the inner ear is composed of the cochlea, the vestibular organs, and the semicircular canals. Okay, so as sound enters the outer ear collects the sound, so it acts like a funnel. Sound wave traveling through an air medium. Of course, around us is air. As the sound travels through the air medium, it hits the tympanic membrane. The tympanic membrane vibrates and it pushes the ossicular chain. So it moves the ossicular chain. The ossicular chain moves around its synovial joints and it amplifies this sound as it enters the fluid-filled medium in the cochlea. So remember, so imagine if you're inside a swimming pool and somebody talks to you from the outside, but you cannot hear it. You cannot hear it well. Why? Because sound from an air medium traveling to a fluid medium gets dampened. Around 90+% of the sound entering the fluid medium gets dampened. And that is the job, alleviating that phenomenon is the job of the middle ear or the ossicular chain. So the ossicular chain actually enhances the sound signal from the air medium outside as it transmits it to the fluid-filled medium in the cochlea. Okay? And in the cochlea, sound, the movement of the stapes against the oval window moves the perilymph within the scala vestibuli. It transmits that sound. The waves of the perilymph forces the basilar membrane to move, and it stimulates the organ of Corti. As we talked about earlier, the hair cells in the organ of Corti is embedded in pectoral membrane. And movement of the hair cells produces action potentials or electrical signals. And these are the ones that are transmitted to the brain. So we have to talk about the tonotopic arrangement of the cochlear duct. What is tonotopic? Meaning that the cochlear duct, so nasa tono siya, okay? So depending on the frequency of sound, different areas of the cochlea is maximally stimulated, or stimulated to its maximum potential. Okay? High frequency sounds stimulate the organ of Corti, displaces the basilar membrane maximally near the oval window. Okay? Near the oval window. High frequency sounds stimulates the basilar membrane and organ of Corti near the base of the cochlea. Okay? And vice versa. Lower frequency sounds produce maximal movements along the length of the scala vestibuli farther from the oval window. Farther from the oval window. So at the apex of the cochlea. High frequency stimulates the base more. Low frequency stimulates the apex more. Okay? So as you can see in this illustration, so probably this sound is around mid-frequency because it stimulates the basilar membrane and the organ of Corti around the middle of the cochlea. Okay? So how is the organ of Corti stimulated? When sound hits the tympanic membrane transmits that mechanical energy through the ossicular chain. The ossicular chain moves the fluids within the cochlea, and the basilar membrane is displaced. The outer and inner hair cells move against the tectorial membrane. Electrical signals are transmitted to the brain, and the brain processes these electrical signals, interprets them as acoustic or sound. So this is another diagram showing you high frequencies stimulate the basilar membrane near the base. Mid-frequency sounds, of course, the middle of the cochlea, and low-frequency sounds near the apex of the cochlea. Okay, so the main mechanoreceptors of the spiral organ are more heavily innervated inner hair cells, but of course, outer hair cells, their depolarization causes them to shorten very rapidly. This is mediated by the protein called prestin because of the word presto, meaning instant. Okay, so piston-like movements of the outer hair cells. So you can imagine pistons, right? Pistons are what's inside a combustion engine. They move up and down. This is also how the outer hair cell looks when it is depolarized. It moves like a piston. It pulls down the pectoral membrane and further enhances the sound by producing what we call cochlear amplification. Okay? Clinical application of this. Okay, we're almost through. Hearing loss. Remember, there are two types of hearing loss. You have conductive hearing loss and sensorineural hearing loss. They're very easy to remember. Conductive hearing loss, of course, the conductive part of the ears, the external and the middle ear. So if you have an impacted cerumen, diseases like acute otitis media or serous otitis media. And finally, sensorineural hearing loss. Usually these are genetic, or if there are any inner ear defects or inflammation of the cochlear nerve, so these can produce sensorineural hearing loss. So the clinical application, you have a cochlear implant. So remember, the cochlea has a tonotopic arrangement. Tonotopic arrangement. High frequencies stimulate different parts of the cochlea maximally, whereas low frequencies stimulate the apex of the cochlea, a different part of the cochlea maximally. And this is what is taken advantage of in a cochlear implant. So if you're wondering, if anyone of you doesn't know what a cochlear implant is, it is not that you get a cochlea from a dead person and you put it into a living person. A cochlear implant is actually a machine. It's kind of like a hearing aid, but it is more advanced and it is more, of course, it is also more expensive and more invasive, but it is also better in the sense that small cables with a series of electrodes, usually around 12 electrodes, is threaded into the scala tympani along the wall containing the branches of the cochlear nerve. Where is it found? In the spiral ganglion. Okay. A device containing a microphone and speech processor on the outside to filter extraneous sounds, and a transmitter is worn behind the external ear. So sounds of various frequencies actually transmit signals to a receiver implanted in the bone and attached to the array of electrodes, stimulating nerve branches appropriate for those frequencies. So it's kind of like mimicking the tonotopic arrangement of the cochlea, because you have different electrodes present along the different, or the entire length of the cochlea. Different frequencies of sound stimulate different electrodes maximally, and thus producing better sound amplification, better frequency selection, okay, compared to a traditional hearing aid. So this is what a cochlear implant looks like. So if you can see here, this is the receiver. So how do you do that? Usually, the otologic surgeon would drill a well at the occipital or parietal part of the skull, put the receiver there, do a mastoidectomy until you reach the posterior tympanic cavity, and then either you do a round window approach or a cochleostomy approach. And then this is the speech processor and microphone and transmitter. So cochlear implant. Okay, that's the end of my lecture. Now class, please study your histology book. Most of the topics I've discussed, but of course there are a few details which you can read more in your textbook. Okay? That's all. Thank you for listening.